Now, moving on through this Heisenberg's uncertainty principle, uh, we would like to attain the concept of zero point energy, and then we will go and discuss the binding energy of electron in an atom. So that should be the case here that we will be applying Heisenberg's uncertainty principle on. So if I assume that there is a particle and this particle is confined to a one-dimensional box of length L. Now, if this is the case, that means what am I doing is I'm assuming this particle is confined. It's confined to move under the influence of the, 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 the potential of some linear dimension that we have here taken as L. Since this particle can exist anywhere in this region, the uncertainty in measuring its position, which we generally take as delta x, can nearly be taken as equal to L, the length of this one-dimensional box. Now, according to uncertainty principle, now if I use this principle here, what's that? That is del px is let me take it nearly equal to h bar by 2. Now, in this case, I'm going to calculate the momentum of this particle in this one-dimensional box, and that's going to be h bar by 2 delta x. So that's going to be h bar by 2l, and and we can take it now. For h bar, we have h by 2 pi times 2l, which is nearly equal to h by l. Okay, avoiding these constants, or we can write down it in the form of this h bar. There's no problem. We can have this thing. So this will give us the uncertainty in the measurement of its momentum. Now, this particle is in this one-dimensional box, so its total energy is going to be the kinetic energy. That's 1/2 of mv squared, because there is no interaction of the particle. There's not any involvement of potential energy. So this can be written as by 2m, and this will be p squared by 2m. Now, for this p, I'll be using delta px squared by 2m. So this energy that we have here is for delta px. What am I going to use is this equation, h cross by 2l. So what am I going to get here is h cross squared by 2ml squared. Now, this is the minimum energy possessed by a particle which is confined in this one-dimensional box. And from this equation, we can conclude that that particle confined to a region of a space cannot have zero kinetic energy. It's confined in a space with no interaction, with nothing. It cannot have zero kinetic energy. It has the kinetic energy. And talking about the physical systems in their lowest energy state, I mean, when its temperature is close to what we say 0 Kelvin, okay, close to this absolute zero. So what we are going to conclude here is that even this particle is at absolute zero. It cannot have the classically predicted value, which is that its energy will be equal to zero. That's not the case. No, here it's clear from this equation. It's clear from the results of uncertainty principle that the kinetic energy of the system or the particle will have some finite value and it will not be zero. This energy that this particle will have, even at the temperature equal to 0 Kelvin, this energy we call as 0 point energy. And to speak the same thing in other words is that a particle confined to this finite dimensional potential is never at rest, not even at 0 Kelvin, because it means px should be zero for this particle, and it should have no uncertainty in the measurement of its momentum. So its p should be zero, then its delta px should be zero, which is not possible. Such a motion that this particle pauses, we call this as 0 point motion. So we have this 0 point motion at absolute zero where the particle has kinetic energy, and that minimum value can be calculated by this equation. Now, moving on to another application of Heisenberg's uncertainty principle is to look. We would like to calculate the binding energy of electron. We have a nucleus, and the electron is around this nucleus, right? So using uncertainty principle, we would like to calculate the binding energy of this electron with respect to the nucleus. So taking the simplest case here is that, let me assume that this atom has an orbit, and the radius of its orbit is r. And so what am I considering here is that the electron is revolving around this nucleus of an atom in an orbit of radius r. Now, as the electron is inside this atom, it is located within this distance, right? The electron is located within this distance. So there is the uncertainty in the measurement of its position, and that uncertainty in the measurement of its position should be equal to the radius of this orbit. It should be nearly equal to delta x. Now, according to uncertainty principle, if I use uncertainty principle, that is delta p delta x is equal to h bar by 2, and so this delta p will come out to be h bar by 2 delta x. So this is h bar by 2r, where r is the radius of orbit within which this electron is revolving around the nucleus. So what can I say here is that hence the minimum value of momentum of electron in this orbit can be chosen as this delta p, and which is nearly equal to h bar by 2r. This should be the case. Now, taking r, we have an average value of the size of an atom, so we can take the value of this r, and which is nearly equal to 10 to the power of minus 10 meters, nearly 1 angstrom, right? So if I do that, I can calculate its momentum, and what's this momentum is h bar by 2r. So this will be h by 2 pi r, and we can use the values of the constants involved and the radius that we have taken, the average value of the radius of the atom. And this momentum that we calculate here is 5.2 times 10 to the power of minus 25 kilograms meter per second. Right. So as this momentum is, we can see that this momentum is relativistic. It's not relativistic here, it's non-relativistic, right? So the kinetic energy of this electron can be calculated. So we can calculate kinetic energy, right? So what will be its kinetic energy? We can see that this momentum is non-relativistic. Okay, so this is to be proceeded. So what would be its kinetic energy? So that will be p square by 2m, right? And we can calculate that using the value of momentum that we have calculated, and taking the mass of this electron as 9.1 10 to the power of minus 31. And this energy that we calculate comes out to be 1.5 times 10 to the power of minus 19 joules. Now, the potential energy of this electron, so you have a nucleus and this electron is revolving around the nucleus. Now, the potential energy of this electron with respect to the nucleus, because it's a bound state, that potential energy is what? So if I write here potential energy of electron, so what is that? That is minus z q1 q2, this is E square by 4 pi epsilon naught times R. This is the electrostatic potential energy of this electron. And giving the values to all the constants here, we will have this potential energy minus times Z times 14.4 electron volts. And we would like to convert this energy into the electron volts, and in doing so we have to divide it by 1.6 times 10 to the power of minus 19. So this 1.5 and 1.6 can be cancelled. This can be cancelled. So we will have nearly 1 electron volt of energy that we can calculate from this equation. So here we have the potential energy of this electron. This is electron volts, right? Now, the total energy of this system is certainly the sum of its kinetic energy and potential energy. So if I take this as 4, so writing down the total energy, yeah, that is, say, E. Here I have used a symbol of E. I should use it as EK, okay, kinetic energy. So E will be for the total energy here. So that will be E kinetic plus the potential energy. And what we have is this EK is 1 electron volt, then plus times this, if we choose this potential, how much is that? This is minus 14.4 Z electron volts. I think I'm right here. Okay, yes, it is minus Z times 14. Is it 14? Yeah, it is 14.4 electron volts. Now, this E will be what? It will be 1 electron volt minus 14.4 electron volt for taking Z equal to 1. Okay, so here we can have the total energy. So what will be the total energy for this? 1 minus 14.4, it's going to give me, it is 14.4 and I have to subtract 1 from it. Okay, so 1.0. So this is 4.31. So this will be minus 13.4 electron volts. Right? So if I take, so for Z equal to 1, it certainly means hydrogen atom. It certainly means hydrogen atom. Right? And if I will take Z equal to 2, and Z is equal to 2 for what? It's equal to 2 for helium. And so Z equal to 2, I will have helium. And for that, what will be my total energy? It will be 1 eV minus 14.4 times 2 electron volts. Right? So this will be 1 minus 8.82 electron volts. and its value, when you'll subtract this, it certainly will be 27.8 electron volts. So see, easily we are able to estimate the binding energy of an electron revolving around the nucleus for hydrogen atom and for helium atom. And for hydrogen atom, it's minus 13.4 electron volts, and for helium atom, it's minus 27.8 electron volts. So there are some other applications of Heisenberg's uncertainty principle that you can think of, you can use of, and you can proceed with. So with this, I would like to end this video. Goodbye, and have a nice time.